Hello, everyone. Welcome to this edition of the broadcast of the Machine Learning in Healthcare Meetup, currently active in Berlin in Germany and in Budapest in Hungary. My name is Vince. I'm the main organizer, and I would like to point out also for the talk later that you can write your questions into the comment section on YouTube, and I can then later show this question in the Q&A session that we will have after the talk. I can show them, and then Mark can answer them. With me today is Adam, one of our co-organizers, and he will continue from now on.
Yes, thanks a lot everyone for joining. I have the pleasure to introduce our speaker today, Marc-Andre Schulz, who is a researcher in the machine learning in clinical neuroimaging lab in Charité Berlin, and also working at the Berlin SFB on workflows for large-scale scientific data analysis. His research mainly focuses on transfer learning, domain adaptation methodologies for deep learning. And with this very exciting speech today, we'll turn our back a little bit on the whole deep learning community and learn basically when not to use it for good. And with this, I'd like to give the stage to you, Marc-Andre. If you guys have any questions, as Vince also said, don't forget to comment on YouTube, and we'll go through them after the talk. Stage is yours.
Sorry, Mark, I think you're still muted.
Okay.
Okay.
Excellent. Okay, as Adam already said, the talk is called The Case Against Deep Learning for Brain Imaging, which of course is a big statement, and of course it's a more of an eye-catcher, and I'm gonna be much more specific, I hope, in the rest of the talk, and I try not to overgeneralize. What my results and our results and our advice is going to be. Obviously, this is not research that I've done on my own. It was done in a large group, and the results that I'm going to show are mainly from this paper that we've published in Nature Communications a month ago. And I think the most important person to mention here is Daniel Stock, who guided lots of these experiments and studies, and who's moved to McGill in Canada now. So let's talk briefly about deep learning, right? Deep learning has a long and troubled history, from the invention of the perceptron to the first actual hardware implementation of an artificial neural network based on memristors. Very early on, the first golden age of artificial neural networks, to the first AI winter, when people noticed that this very simple logical OR function can't be implemented with a perceptron, which was a bit of a letdown for lots of people, to the second rise of deep neural networks, where backpropagation was invented, right? Q-learning, CNNs are first mentioned, but it turned out that support vector machines were actually pretty good and pretty competitive at that time. And again, a bit of a letdown to see that all these great methods didn't achieve their full potential yet, and were, again, for like 10 years in the second AI winter, as people call it sometimes, overshadowed by kernel support vector machines then, right? And then only recently, something like 10 years ago, we got the real deep learning explosion, the real rise of deep learning, where I think mostly fueled through the availability of very powerful GPUs and lots of compute. Things that have been invented a long time ago suddenly started to achieve their full potential. And when I say full potential, I can obviously mean something that I don't know how many people have anticipated this, but essentially human and superhuman performance in lots of different areas, right? From image recognition, which I think most of you are aware of, where we have surpassed human performance on the image recognition in at least the CFR10 dataset here. The blues above the human performance dotted line are what you would like, if you want to call it like that, superhuman performance. To gameplay, right? Computer Go, deep neural networks have beaten the world's grandmasters at Go. Same thing goes for lots of other video games now, right? Lots of Atari games have been beaten, and humans are not able to compete with the machines anymore. It goes further to natural language processing, right? Question answering data sets, acoustics, sound, speech recognition, human speech recognition here. Also, at least on some data sets, human or superhuman performance. And in the area of biomedicine, we get this nice Nature cover here, lesions learned, where we get at least dermatologist level classification of skin cancer with convolutional neural networks, right? So it works in a variety of different areas. And obviously there was quite some excitement regarding the question of how well deep learning will transfer to the analysis of brain imaging data, right? Because if it works so well in all these other areas, then there's a reasonable and a reasonably high expectation that we can also get something out of this for the field that I work in, for brain imaging data. So I know that in the audience, there's supposed to be a mix of machine learning experts and people who maybe come from more of a, have more of a clinical background. So I'm trying to give like a very bird's eye view on both the machine learning side and the neuroimaging side, and not go into too much detail. But I think for people who are unfamiliar with brain imaging, or at least the MRI-based brain imaging that we do, I should show what kind of data I'm talking about, right? So I'm in this talk, and in the paper that I'm mainly presenting, we have reduced our analyses to what we consider the most common sorts of MRI, which is like magnetic resonance imaging based brain images, which are structural images, where we're looking at gray matter, white matter, mostly gray matter distribution in the human brain, and functional MRI, where we are broadly speaking taking a video of brain activity, and the way that this is then usually analyzed in many cases is by parcellating the brain and looking at the activity over time in these brain parcellations, and from that constructing something like a connectivity matrix, which is essentially just kind of the correlation between the temporal activity between these brain regions, right? So this is broadly what lots of people use, and this is what we're looking at in this paper. Now, these are the features, right? This is the input data, and we also have to look at the tasks that can be performed on this data, right? The classification tasks, the potential prediction targets. And here I need to distinguish two categories, right? The first of these categories is the category of things that a human being can easily do by looking at these brain images, which includes most prominently the identification and segmentation of lesions, of tumors, for example, right? As you see in the images down here, right? This is something that a human being can identify in the image. And this is therefore essentially a computer vision task, right? A computer vision object detection task. And this has to a large extent been solved, as I already said, right? With the image recognition, same goes for image segmentation. And that also consistent with these expectations works really, really well. But there's a second category of prediction targets where it's really not trivial visually for anyone to make this decision as a human. When we are, for example, asking, does this particular person have schizophrenia? Or how old is this person? Or is he maybe at risk for depression, right? This is something that you can't see visually, directly, intuitively from a brain image. And there, the expectation and the hope is that deep learning, which is able to model very highly complex, high-dimensional, nonlinear interactions, could have an advantage over human beings and allow us to predict things, infer things that have been inaccessible to scientists in the past, right? So there's lots of excitement, and it was a very high expectation when I personally started doing deep learning and brain imaging, like what, 3 years ago now. But this excitement was mixed with lots of controversy. I have here on the right a couple of my favorite quotes with regards to deep learning for brain imaging data, right? Starting with this very general, despite the success of deep learning, the superiority of this analytical approach in neuroimaging is yet to be demonstrated, right? That was a review paper from 2017, where they already came to the conclusion that there wasn't a clear win yet. There wasn't yet a clear win declared for deep learning for neuroimaging, right? It was kind of too early to tell whether these methods were as powerful and as useful as we expected them to be. Then secondly, there were lots of challenges, competitions for brain imaging, for predicting Alzheimer's, fluid intelligence, and I think age is the third one, where there were very high hopes for deep neural networks, for CNNs, 3D convolutional neural networks, and then kind of blowing the traditional, the classical machine learning out of the water, but that also didn't materialize. And surprisingly, in most of these competitions, very standard machine learning models, right? Trees, random forests, kernel methods are very competitive and often beat, or even usually beat out the deep learning approaches, right? It goes even further with the controversy, right? We have authors here, Amaya Lindenberg, observing that the counterintuitive negative correlation between model classification accuracy and sample size. Now, this is scary, right? And here's two plots from the literature, because sure, there are positive results in the literature, right? Sure, there are people who have shown very nice accuracies with very complex machine learning approaches, but people who looked at these studies from a bird's eye view, compared them, oftentimes came to the, I think what there's 3 studies mentioning this, came to the conclusion that even though you would expect accuracy to improve with sample size, given the studies that we see, there seems to be the inverse relationship, and prediction accuracy actually decreases with prediction size, right? Which makes you suspicious that something is going wrong. Lastly, there's the quote here from the single subject prediction of brain disorders in neuroimaging review, that comparison of accuracies between studies is essentially meaningless at this point in time, right? And they argue this meaninglessness mainly, firstly, because we don't really have benchmarks, clear benchmarks to compare models and modeling approaches on, because people tend to use vastly different pre-processing pipelines. Sometimes the image resolution is different, right? And prediction targets vary widely. So it's actually not clear to what extent these accuracies can actually be compared. And then when you're wondering to what extent deep learning might have an edge, very few of these papers have report linear baselines for comparison. And often, and this is not a brain imaging problem, but I think it's a machine learning problem in the whole field. Oftentimes, these linear baselines are not tuned to the same extent as the deep models are, right? You have to imagine that there's people throwing lots and like weeks on end of fine-tuning into their deep learning approaches, and then they run a very simple run-of-the-mill logistic regression or something, and I think in many cases, can't reasonably claim that this is the best that the linear modeling world has to offer and that this is a fair comparison, right? So that when I started working on this, I think I wasted a year on trying to get, for me it was semi-supervised deep learning approaches to work on the brain imaging data, in this case from the UKBiobank, fairly large data set, 10,000 images. I couldn't get anything to work, right? So I slowly got sucked into this camp of skeptics. And I think my advisor, right, Daniel Stock, also had this intuition, and he pushed me to try to figure out what's going on here, right? So we started a larger scale benchmarking study of this. But our intuition was, our hypothesis was that maybe there's something going on with the data, right? That maybe the issue was not that we haven't yet found the correct deep learning approach, model architecture, but that maybe the data itself is at fault. And maybe there's something wrong with the data, or we have not enough data. And there's a principled reason, in a way, for why people haven't had great successes with deep neural networks up till now, which have like clearly settled this question on whether or not you should deep learning to analyze brain imaging data. Now, the problem that we have, obviously, is that we're trying to prove a negative, right? And that's always really, really tricky. So the issue is that if there's something wrong with the data, we would like to show that with some confidence. And if we would just compare, let's say, linear models and deep neural networks, then at each point in time, no matter which model we try, someone would come up to us and say, but you haven't tried let's say, this particular architecture, or that particular architecture, or how about this, right? Because the problem with deep learning is the fact that, and honestly, I mean, usually this is called the beauty of gradient-based learning, that you're not really constrained to a particular architecture or a particular model. You are insanely flexible in your modeling, right? This model zoo here is a nice illustration. You could pick like each and any of these architectures. You could change them around. Anything's possible, right? On top of that, there's an infinite list of hyperparameters that you have when you build artificial neural networks, right? The learning rate, optimizer choices, learning rate scheduling, batch size, how you initialize the weights, the loss function that you choose, how the model looks like in detail, right? How deep it is, how the layers look like, the layer size, the number of filters if you're talking CNNs, the kernel sizes, the pooling. Maybe you have max, maybe you have max pooling. What stride should you choose, right? Should you have batch norm? Shouldn't you have batch norm? How do you regularize the net, right? The list goes on and on and on, and there's just no way to comprehensively benchmark deep learning for brain imaging in that way, right? So we had to figure out something else. And what we ended up with was the following idea. The reason for why we would like to use deep learning is because of its ability to model highly complex nonlinear interactions, right? That's what we're looking for. Because if it were just simple linear relationships in the data that we were looking at, we wouldn't bother with them. We would just do linear modeling because it's the simplest and the most effective, right? So the basic prerequisite for deep learning to make sense is that there needs to be exploitable nonlinear relationships in the data. There need to be some predictive nonlinear relationships in the data that we can extract with the sample sizes that we have at hand, right? So our idea was to use, between the linear models and the deep neural networks, a surrogate model category. For example, kernel support vector machines. For example, a support vector machine with a radial basis function kernel. Because oftentimes people say, oh, but the great thing about deep neural networks is that they are universal function approximators, and they can approximate each and any continuous function, and that's like a benefit in of its own, and other models can't do that, but turns out lots of other models can do that. For example, the RBF SVM is perfectly capable of modeling any continuous function that you throw at it with sufficient training samples, right? So what we're saying here is we are using surrogate models, not with the perspective to use them in the end and to get great accuracy or anything, but just as a microscope in a way, as a measurement device to confirm the existence of exploitable nonlinear relationships, right? If they are like strong exploitable nonlinear relationships in the data, then the kernel SVM, for example, should be able to pick up at least some of them, right? They should be able to show us at least the existence of exploitable nonlinear relationships. And that would make us more confident that the data is not as fault, that there is something in the data that we can use, and maybe we just need to fiddle around with the deep networks a bit more, right? So this was the idea that we had, and the study setup in the end looks like this. We take our input data, we take a couple of machine learning benchmark data sets for comparison, and then we take different types of brain imaging data, and we pipe them through different model classifier categories, right? We start with simple linear models, and we always take a variety of different models just to be sure that we don't make a mistake with a particular model, or that one particular model's inductive bias is problematic or doesn't work well with the data that we're looking at, right? So we start with linear models, move on to nonlinear models, kernel methods, and end up with deep neural networks, fully connected and convolutional deep neural networks. Now this looks still kind of simple, but you need to consider that we want to do this well, right? We want to be reasonably confident about our results. Therefore, we can't just check these accuracies once for one particular sample size and be done with it, but we want some measure of uncertainty, right? So we are going to resample a couple of times, usually 20 times, the train and validation and test sets. Then we want to be sure that that the conclusions that we arrive at hold true for lots of training set sizes, and not only the particular one that we picked. So we're going to do this for lots of train set sizes. Now, obviously, we need to do hyperparameter tuning, and to make this really clean and conform to best practices, we're going to do the hyperparameter tuning for each of the resamplings and for each of the train sets again and again and again, right? And then we do this whole thing for each of the models that we look at, and then we do that for each of the prediction targets that we are analyzing, and for each of the features, or the model inputs that we're piping through here, right? And if you multiply all of those, you end up at multiple millions of trained models. So it was more, at least for me, more of a high-performance computing challenge than anything else, because that was something that I wasn't trained to do beforehand. To get the most of this, we calculate these what we call empirical sample complexity estimates, right? Of course, these are not the sample complexity analysis that you usually get from statistical learnings, from statistical learning, which are theoretically derived. But this is our approximation for what the sample complexity looks like for a certain data set, for a certain prediction target, given a certain model and well-tuned hyperparameters for each of these sample sizes, right? I'm showing this to you just to point out a couple of interesting effects that you see when you make these sample complexity analysis for different model classes and combine them together in this kind of view, right? The first thing I want you to keep in mind is stagnation. What you see here that the linear models start increasing in performance, improving in performance with all the others, but then they stagnate, right? And they converge to some maximum accuracy that they're not going to beat. This is important. The second effect is expressivity. What you see quite nicely in this picture is that the different model classes have different expressivity. They have different abilities in modeling complex interactions. The linear models have kind of achieved the maximum of what they can comprehend at, what is it, around 88% of accuracy on the MNIST digit classification task. But the kernel models are much more expressive, right? And you get much higher accuracy. The last thing that I want to point out is this here, right? You see that the convolutional neural networks have a bit of a head start in this analysis, right? They start off very early for very few training samples with very high accuracy, and that is because of their inductive bias, right? An inductive bias is the lens through which a model looks at the data, and the particular inductive bias of convolutional neural networks is translation invariance, right? Is having filters that are generally applicable to every point, to every location in an image. And that particular inductive bias works very well for this input data, for these digits, because they can easily be translated a couple of pixels to the right, a couple of pixels to the left, shifted, maybe slightly rotated, right? Therefore, this is a powerful inductive bias, and therefore it gives them, these models, a head start over the others. Keep these things in mind, and now when we now look at how these types of plots look like for brain imaging data and get to the results, right? So here's, in a way, the summary and the gist of results. On the left-hand side, we have our machine learning benchmark data sets, right? MNIST, and here we have fashion, which is essentially the same as MNIST. It's a bit harder drop-in replacement for MNIST, and instead of digits, you have different types of clothing, 10 classes of clothing. And you see, right, as you would expect, as in the last picture, the linear models perform worst, they stagnate, converge very early on. The nonlinear models, the kernel models perform much better and get topped out by the convolutional neural networks, right? And at the harder fashion task, you see the same effect, right? You see linear, nonlinear, deep, and you see stagnation, and you see that this stagnation of the linear models happens a bit later than for MNIST, which we suppose is due to the higher complexity of that data set, right? So that's great. That kind of confirms, the left-hand side confirms the expectations that we have with regard to these models and the complexity, or the difficulty of the prediction tasks. Now, what we did here on the right is do the same thing for brain imaging data, and we tried, just for having a nice and direct comparison between these two sites, to keep it close to the MNIST parameters, right? So we use imaging-derived phenotypes, IDPs, from the UKBiobank. The whole set of brain images is from the first brain imaging release from 2017 or something from the UKBiobank, where we got, at that point, fairly large, I think at this point, the largest brain imaging data set of 10,000 brain images. We used 8,000 for training, 1,000 for validation, 1,000 for the test set, right? And these IDPs, as I said, are imaging-derived phenotypes. They are for the structural MRI. These are like gray matter densities, and for the fMRI, it's the functional connectivity that you saw in the plot earlier. That is quite nice because the feature dimensionality of these IDPs for the structural brain image and the functional brain images is like within an order within an order of magnitude of the MNIST and fashion feature dimensionality. So it's broadly comparable, and we're constructing a prediction target that is also comparable by taking the age and the sex of the participants, combining them by kind of binning the age into 5 bins, combining that with the sex also gets us a 10-class classification task. So now we have broadly comparable tasks to the MNIST and fashion task. We run all our models, and we would expect, as here, right, the kernels and the deep nets to outperform the linear models. At some point, we would expect a stagnation of the linear models at some point, but we see nothing like that, right? We see no clear stagnation of any of these model classes whatsoever. I mean, of course, you need to, I'm perfectly aware that this is a logarithmic scale, right? And the increase in performance is slowly getting smaller, and you need to add more data to get the same percentages, the same amount of percentage points in improvement. But still, if you are willing to collect like an additional 8,000 data points, you're going to end up here, it looks like, right? And if you're willing to get an additional 16,000 data points, at least if we can extrapolate, you should end up somewhere here, right? So the brain images look completely different. There's no differences between the model classes whatsoever. There's no stagnation. None of the intuitions that we had and that we saw confirmed for the machine learning benchmarks materializes. And now we get into the what about game, right? Where the reviewers reasonably, and ourselves, of course, and colleagues said, but maybe it's because of the features that you chose, right? So we played around with the features, and we tried all sorts of things. We tried just slices of the brain images that we fed into the CNNs and the models. We tried the raw voxels, the gray matter masked voxels of the structural MRI. We tried that with smoothing, without smoothing, in different varieties, and it had no effect, right? The only interesting effect that you can see here in the figure on the right, where we compare the performance of these models on brain slices, coronal brain slices, with and without smoothing, is that the convolutional neural networks outperform the linear models in the unsmoothed data. But they perform at exactly the same level as all the other models perform for the smooth data. So what has happened here? What has happened is that the convolutional neural networks have learned the optimal smoothing kernel right? Essentially, they have learned how to smooth the data to get to the same results that the linear models can get for the smooth data, which is like nice and fun, but it's not really the effect that we're looking at. What we're looking at is something here, right? The deep neural networks start to outperform other models in a more meaningful way. But maybe other people say it's about the targets, and that's a fair criticism, right? We have artificially constructed a target variable here. Maybe that's a weird one. So we disentangle that again. We run all of these analyses again for age regression. We run all of these analyses again for just binary sex classification. We run it for a variety of other targets, fluid intelligence, household income, household size, that we know have kind of predictable information in the brain, in the fMRI, and for none of the target variables that we looked at could we see an improvement of nonlinear models over linear models. The best thing that we saw model-wise always was ridge regression, essentially, right? Ridge regression or regularized logistic regression. That seems to be the best thing that you can do. Maybe it's about the dimensionality, right? Sure enough, we didn't fully match the MNIST dimensionality in this first plot, so let's try to do it. Let's try to do feature selection, univariate, recursive feature elimination, random projections, PCA. In none of these scenarios could we see a difference between linear and nonlinear models. Take a look at this PCA matrix here, right, where we have different data sets. The MNIST again, fashion. Here's a new one. It's histology slices. This is essentially kind of related to the cancer, skin cancer detection that I showed you on the Nature cover in the very beginning. And for all of these benchmark data sets, there's a clear difference between the green and the red, between the linear and the nonlinear models, right? You can't miss it. But if we move on to the brain imaging data, raw voxels, fMRI, SMRI, IDPs, none of the models differ from each other in any way that we can measure. This is really curious, right? But maybe it's the model choices, people say. And so we tried trees, right? Random forests, extra trees, gradient boosting. Nothing seems to help. We get exactly the same result. And honestly, now we're kind of out of high-performing nonlinear models, right? All the SVMs, all the tree-based models, the gradient boosting. It's unclear what else we can do model-wise to find this confirmation of extractable nonlinear structure in the data that we've been looking at. Maybe people say we fucked up the hyperparameter tuning. But we reran the whole thing with Bayesian hyperparameter search here on the left, and nothing changes. We double-checked and visualized each of the model grids and the model's performances. The hyperparameter grids and the model's performances on these hyperparameter grids, and they all look perfectly reasonable. So that can't, at least we're reasonably sure that won't be it, right? But maybe we made a mistake, people say, because the nonlinear models, right? They are very complex. They are highly expressive, and we are only giving them a very small number of training data. So shouldn't they underperform at least somewhere in comparison to the linear models? Shouldn't it be more like this, right? That the nonlinear models start off terrible, but then beat off the linear models at some point. And that's a reasonable intuition, but when you look at the models that we're using, all of them are, especially the kernel SVMs, are regularized, of course, right? And what happens is that if you tune your hyperparameters correctly, and there is only linear structure in the data, maybe because there's maybe because there is no nonlinear structure, or maybe because the nonlinear structure cannot be exploited because you don't have enough samples, right? Then it turns out the most efficient hyperparameter combination usually turns out to be the one that reverts to the linear model. And we can make this very explicit for the RBF SVM, right? Down here, I have the kernel, the radial basis function kernel. And now let's look at, for example, MNIST or fashion. And the bright dots here are the models with the low train, with the small train sizes. And this should be like 100, 200, 500, right? And what you see is that for the training sizes in which there isn't a difference, even in MNIST, between linear and nonlinear models, right? Because if you remember correctly, they started to diverge, I think, only at around 700 or 1,000 training samples. So for this regime in which there is no difference, the best hyperparameter for the gamma, this hyperparameter here, is really extremely tiny, right? 10 to the minus 20, 15 or something. And now if you look at the kernel and think about what that means, it means very tiny gamma. It means that we're essentially in the area of around 0. And if you approximate the exponential in around 0, you get, what is it, 1 plus x, right? So what we've kind of demonstrated here very simply is that for small train sizes, the RBF SVM reverts to the linear special case of this exponential kernel. So all of that seems to be in order, right? And you see the same behavior for the other kernels as well, that essentially in the absence of exploitable nonlinear structure, they just revert to their linear limit, to their linear counterpart, essentially. Okay. So I'm kind of out of potential criticisms. I don't really know what else to say. So let's discuss what we've seen. We have seen no exploitable nonlinear structure, right? No evidence of exploitable nonlinear structure. We haven't seen a single instance in which a nonlinear model outperformed its linear counterparts. That is strange, right? So there's two potential reasons for that. The first is we just don't have enough data. That might be, right? And the second, the scarier one, is that maybe there is no exploitable nonlinear structure in the data. Maybe we could throw samples at it, as many as we want, we wouldn't make this any better. Now, the question is, can we figure out which of those is true? I mean, not trivially, but we can kind of investigate further how these sample complexity curves can be interpreted, right? The second thing we saw is the continuous improvement of linear models, right? You see that the linear models, all of the models still improve in performance if we add extra samples. What does that mean? That means that even the linear effects, even the linear separating hyperplane of a linear model cannot be yet fully characterized, right? Essentially, this tells us that all these models are making an estimate for which the best separating hyperplane is, but oftentimes they're wrong. There's lots of sampling noise going on. They make mistakes, and therefore the prediction accuracy is bad, right? And the more samples we get, the more certain they are with their characterization of this linear hyperplane, of this decision boundary. And the more certain they get, the higher the accuracy, right? But given that they are still improving, we can infer that they don't yet have full confidence on how this decision boundary looks like, right? On where it is, on where this hyperplane is oriented. And I think that directly tells you that if you can't even be sure what the linear hyperplane looks like, what the hyperplane looks like, what the linear decision boundary looks like, then what gives you the confidence or the expectation that you should be able to characterize much more complex nonlinear decision boundaries, right? So essentially, this lack of a convergence of linear models gives us a further indication that we shouldn't even expect nonlinear models to outperform the linear ones, right? Because if you can't characterize the linear decision boundary, why should you be able to characterize the nonlinear decision boundary? So now we have kind of two levels of intuitions for what is happening and what is going on. The first thing is we shouldn't even expect the nonlinear models to outperform the linear ones. We don't see the nonlinear models outperforming the linear ones. So either there aren't enough samples or we don't have nonlinear structure in the data. We hope, of course, all of us, that we just need more samples, but there's a certain fear that we have that it might be the data. This fear comes from this sub-analysis. What we did here is we took the MNIST data, right, where we see this very clear difference between linear and nonlinear models, and then we just added noise to the features. Added noise, more noise, more noise, more noise, more noise. And the surprising and scary thing that happens is that if we add enough noise, our sample complexity estimates look eerily similar to what we see for the brain imaging data, right? Which is that there's no convergence that we can observe for linear models and no difference between linear and nonlinear. That is pretty scary because it suggests that it might be the case that the data is too noisy for us to actually exploit nonlinear structure in there. What does it mean that we can't exploit it? Yeah, maybe we can't exploit it at all. Look at this. This is a simple illustration of a two-class classification problem where we have the red dots and the green dots, right? Two mixtures of Gaussians. And we are adding measurement noise, essentially additive isotropic Gaussian noise to these red and green guys. And down here we have the decision boundary. I mean, this is the equiprobability, so it's the difference between the probability of red and the probability of green. And usually you say decision boundary is where they're both equally probable, right? And you see that, I think, quite nicely here, where you get this U-shaped decision boundary, right? So you would kind of separate the reds from the greens with Uppsala with this decision boundary. And what you see here in the illustration and the simulation is the more you increase the noise, the more linear this decision boundary becomes, because essentially, at least this is our intuition, what you get is two big Gaussians, right? A big red Gaussian that unites the two of them, where you can't where you can hardly distinguish the constituent sub-distributions, and a big green Gaussian, and the separating hyperplane between the decision boundary between these two is always linear, at least for like isotropic noise, right? In the worst case. And the greatest fear is that something like this is happening. We don't know yet. We're looking into that. This is kind of what I'm mostly concerned with at the moment. But this is like the worst case scenario. Finally, let's briefly discuss CNNs, right? Lots of people think, oh, convolutional neural networks should work great. But I've already talked about inductive biases and the inductive bias of translation invariance that CNNs have. And that is great, right? If you take a natural picture of, I don't know, a face, right? That face might be anywhere in the picture. And a CNN taking care of that translation invariance is going to perform much better than linear models, which would have to detect faces kind of manually everywhere in the image. But for brain images, we do lots of preprocessing, right? We put them all into the same space. We invest lots of effort to make sure that they look exactly the same, that they are in a comparable reference frame. And we don't really have to go and look for the amygdala or the hippocampus, because after this registration of brains that we do to a standardized space, there's no need to look, right? We know where they are. So it's unclear to what extent this inductive bias of translation invariance is actually going to help us for like well pre-registered images. So this is all I have for the discussion. So the final thing that I want to mention is what you should do before using deep learning, before taking this very complex machinery of deep learning and applying it to your problem. the first thing I would suggest is to run a sample complexity analysis, an empirical sample complexity estimate with a couple of simple linear models. And if you see that these linear models are not saturating, then you have a good idea about the fact that the linear decision boundary can't even be sufficiently characterized, and you should not necessarily expect nonlinear models to perform well on that, right? If you want to be sure, run an extra analysis on, let's say, an RBF SVM or some other nonlinear model, right? If you see a clear difference between the linear and the nonlinear models, if you see exploitable nonlinear structure, then there's a good chance that you might find a deep learning model which has an inductive bias, which works even better on the particular input data that you have than the kernel SVM, right? So then it makes sense to look and design a great deep neural network. But if you see no stagnation and no difference between linear and nonlinear models, then there's no clear indication that exploitable nonlinear structure even exists. And then you should be very skeptical, at least from my point of view, on whether or not you should apply deep neural networks. Okay, that's, I think, everything from my side of from my side of the screen.
Marc-Andre, thank you very much for this very, very interesting talk. Yeah, so we will start the Q&A session. There were, I think, 2 comments that were raised during the talk. If you have more comments, questions, please write them now. I'm just gonna start from the beginning. So there was a comment relatively early in your talk. Linear models cannot outperform neural nets. It's theoretically not possible. Was probably related to some part in the introduction.
I mean, that kind of depends, right? I mean, that's also a pretty broad statement, because surely a terrible deep net can be outperformed by a well-tuned linear model, right? I mean, just simple counterexample, you're going to overfit your deep neural network. And I have a well-regularized linear model. That statement might be sure in the absolute best case, in which you have ensured that everything goes wrong, and that nothing goes wrong, and both instances of models are perfectly fine-tuned. But I don't know how often that is the case. And honestly, I have the feeling that it's much easier to prepare a linear model and make sure that that works well, and that it is fine-tuned and well-validated, than to do the same thing for a deep neural network, right? It's much more complex. You need to invest much more time, much more debugging, more things can go wrong. So I think there's actually a fair number of instances in which your linear model is going to outperform the deep net.
Thank you very much. There's another question here. Did you try non-preprocessed images for deep learning? What you mentioned is not necessary for deep learning, is it?
So, of course, these are pre-registered data samples, and that's a very good and reasonable question, because if you would take the absolute raw image, right, then you would have, intuitively, you would have more and more trivially exploitable nonlinear effects in there, right? Because the images would not be aligned, they would not be of the same size, they might be slightly rotated, and all of these would call for nonlinear corrections. So yes, if you would run the same thing on raw MRI images, then the deep nets would definitely, and I'm pretty sure about this, would outperform all the other models. But the point is that we have already invested decades into figuring out how to do these particular nonlinear corrections really, really, really well, right? And we can do them easily, and they're well validated. So the question is, would that be a fair comparison, right? Why would you ever do that? It would be in a way like taking the linear models and making it kind of arbitrarily hard for them to compete, when you could just as easily give them the benefit of the nonlinear corrections that we already know and apply on a day-to-day basis.
Maybe a comment from my side on that. There's, of course, what you would say is right, although some of these methods actually have problems when you have big lesions in the images, then they start to fail, because then the images are so different, right, to the like the normal brain that is normalized. So sometimes I think that could be maybe an application where this could make sense. Also, we always have to keep in mind the time in the clinical setting. So how long does it take? Some of these classic preprocessing methods take a long time, and they have to run on a console, like on an MRI machine. So these are maybe just from my side some reasons. So we discussed this internally a lot, and I later also have a question, because there's something that really is on my mind. But
I'm absolutely on your side there. So for preprocessing, I think deep neural networks make a lot of sense, and that's maybe I should have been clearer in the beginning, and probably I wasn't, if I think about it. But that's what I meant with these two categories of tasks. So I think detecting lesions, I think pre-registration of data, I think scalp stripping, these kind of things are absolutely, in a way, computer vision tasks for which we can leverage deep neural networks, and for which I would expect them to perform great. And I've actually used a UNet-based scalp stripping now a couple of times, and it works really well, right? So that's why I'm kind of trying to delineate these two different types of prediction tasks, because I think there's a crucial categorical difference between the two, in the sense that one of them are clearly computer vision tasks, and the other are like a much more nebulous search for some form of not clearly defined high-dimensional nonlinear interaction, right?
Yeah. This is very good that you mentioned that. So this was my question for later. So sorry guys, quickly, because it fits. I'm gonna ask it now, because this is exactly what we see also in our lab. So for example, segmentation tasks using a UNet, it's incredible how well it works. You need like a few examples. You even do like sometimes you can even do like one brain. It's not one shot, but lots of patches. But you can do one brain learning, how I would say it now, and you can basically you have already a much better segmentation result that has been achieved in decades of other methods. It's incredible how well it works. And then you take the same images and you try to predict some simple thing like age or a clinical outcome, and it completely doesn't work anymore. It's like, so I agree with you, there's a fundamental difference, and then you see, basically that was your answer, so now I just agree with you. There's a fundamental difference between, and very nice how you said it, is computer vision task, like here are hyper intense voxels, find them because this is relevant. Mm-hmm. And this very nebulous, as you said, the thing like age, clinical outcome, where we simply fail, and we know from many other groups that try the same, it's not working. And we're really trying to figure out now what the reason is, and we also don't have an answer yet. But there were more comments. So the next one is, there's a tacit assumption that ML can help address weaknesses in measurement methods. How would you address this assumption?
I'm not entirely sure I understand the question.
Now that I read it, I'm also not sure. Maybe you can, the person who asked it, maybe they can elaborate in the chat, and I'm happy to then re-ask the question. The next would be, can you explain a bit better what were the target classes for structural MRI? Would you expect the same for segmentation of brain lesions, for example? This kind of touches on what we said, right?
Yeah. So I think the rule of thumb here would be, could a human do it, right? And I think lesion segmentation, humans do it, right? Scalp stripping, if you really want to, you can do it by hand. But figuring out if someone has schizophrenia from a functional connectivity matrix, just by looking at it, not a chance, right? And I think this is probably the qualitative difference of what we're looking at, right? There's a lot of problems that we would like to throw machine learning at, specifically because we don't know how to do them. And I think that's the danger that we need to keep in mind, right? That we've grown so used to the successes of deep learning, particularly in computer vision, but we need to always keep in mind that these are things that we know how to do, that we can do, that we understand how they're happening, that we can label, that we can validate, right? Where, like, for example, with schizophrenia, we don't even have reliable labels, right? It's not even entirely sure how to categorize these people.
This is a very good point that you touch upon, because the same thing that we have in our stroke analysis, the label is not good and the label is noisy. So we have a priori a bad label. So basically we have kind of what you touched upon, maybe noisy images, and we're trying to predict a noisy label. So maybe if we phrase it like this, it's not that surprising that it's not working that well, or that we cannot exploit what they are good at. Let's put it that way, right? Very, very good point. So the next one. Doesn't the fact that the accuracy is still steeply rising at 8,000 suggest that you simply need more training data to make a point? Did you try data augmentation?
Yeah, no, we didn't try that. It's kind of that goes into the shopping list of design choices and hyperparameters that you could play around with. But yes, that's definitely true. And that is what I am most interested in, right? I'm going to replicate this thing on the new UKBiobank release of 40,000 people and see what happens. And I'm really curious about how that's going to turn out. If we're just going to reach a sample size at which we can detect these nonlinear interactions, or whether the same pattern is just going to continue. And we need to focus maybe a bit more on investigating the impact of noise on this particular classification problems.
So we have something to look forward to, and it means that soon we can re-invite you then for the update talk about the extended number of patients. This was a very, very interesting talk, and I think I also very much like the discussion that really touches upon kind of like a very deep philosophical, so to say, question: when to use which methods, and not to just do analyses based on the hype created by the media, but really trying to understand the methods in depth and to define then the use cases, because this, of course, leads to enormous waste. If you try to use these very, very complex methods in a task where you don't even need it, or it will never work, and you could achieve similar or maybe even better performance with easier methods, then translational efforts might fail, startups might fail. This is a huge waste of resources. So this is really also a problem that we need to tackle to actually better understand when to and when not to use when to use them or not to use these methods. So I'm sorry, running out of time. So sorry, maybe you can also contact Marc-Andre directly. I saw there was now an update, but we are also over time. So that was a comment. Thanks for the talk. And I really can just say thank you very much again for the talk. It was a pleasure. Thank you guys for tuning in, and see you at the next meetup. Thanks a lot. Bye-bye.